All right, so hello and welcome to this video. In this video, I'm going to show you how I decoded an AI model and what are my findings. So this is part of my hobby project Phygineer research. And let's dive in. So I've divided this into three parts. So these are the topics that I've explored eventually when I was experimenting around the model. And in the part one, it will be mostly covering the internals for a model file, like actually safe tensor model file, and then a couple of tools around it, and then the blueprint of it. The second part will be mostly focused on the VRAM problem, like how this quantization works, and then the brain surgery, where we actually decode the model uh, and inject few things into neuron, modify few stuff, and then see the output. And then there is this third part, which is like demonstrating AI immune system, mind control, and Polysemanticity. So, and the model collapse and Goldilocks zones and all of this stuff. So, this is like a practical thing that I did. I just took a safe tensor file from Hugging Face and then I decoded it, looking at the hex editor, extracting the data from hex editor, then looking at the vector sizes and other stuff. So that's all the experiment is around, and I just documented it in the presentation. So I'll be probably also creating GitHub pages for the source code of the Python script that I've used. And we'll also put this PPT somewhere so it will be public. All right, so let's get started. So part one, internals of a model file. So this is the basic thing that I wanted to understand, like how exactly model works. When you say there is a model loaded into memory or we have downloaded the model and we'll be running it on our system, when you say the model is downloaded, then it's a file, right? Like a zip or any other file, basically. So in our case, it will be from huggingface.co. You can see I'm using this. And as soon as I write this code, it will eventually pull the model and download to my system. Okay, once this program executes. So this is how it looks like. So this is my username on Mac. I'm using Mac. So you can see on this directory, this is the model name, Hugging Face SMOLLM2. So I specifically decided to go with this model because first, it's the smallest model that I could find, which is relatively good. And its size is 135M. So sorry, its size is really small, 256 MB RAM. And then the parameters, you can see 135M, million parameters, right? So a really good and decent model. And here is the directory listing of that. So whenever you pull something from Hugging Face, it stores it in the cache directory inside the username. And then you have to go to navigate to the path inside it. And you will see this file, model.safetensor. So this is the file that I'm talking about in this video. And if I look at this -lh option, it shows me this file size as well. And for particularly model safetensors, right, you'll be able to see it's 76 bytes. And what happens is I'm inside this directory, snapshots. So inside this directory, we actually have links, which takes us to blobs. So you can see these are system links, sim links we call them in Linux, I guess. And this model.safetensor, that's why it's only 676 bytes in size, but it's actually pointing to this blob. So when we actually see the size of that blob, then you can see the size of that blob is 257M, that is 257 MB. So that's it. That's the model file and that's the model size. Now I dig deeper into that. So you can see I've opened that model safe tensor file, and this is how the decoded text look like. So I'm using this VS Code hex editor plugin where I right click on the model, open this directory, and then you can see this is the initial. You can see this JSON start, and then there is some metadata. So all this metadata is actually I'll tell you what it is, but after that is done, then there will be like actual brain of model, we can say. So I use VS Code hex editor extension for this, and this is how it looks like. And initially there is metadata about the model, and then there is the actual model brain, which we are interested in. So as you can see, after scrolling a while, you can see here that JSON ends, and then this is where the brain starts. So this is the like, actual model. All right, so that's about the model file stuff. So this is how safe tensor files look like usually, and then they might have different kind of JSON formats and other stuff. Again, you also have to be careful about which encoding you are seeing the text into. So all those kinds of things. So yeah. So let's dive deeper into this model file. But before that, let me just show you. I'll just go ahead into the slides and I'll show you this. So this you can see, right? So in that JSON that we in that JSON that we saw before. So this JSON, I actually extracted it and then converted it to this sheet. So this is how it looks like. So you can see initially there was global category and then there was layer 0. So this model has 30 layers. So 0 to 29, which will be 30 layers. I've explicitly marked some of the layers hidden to capture the screenshot. And you can see the total size that way, 269 approx. So 134 parameter size. So 135 M, we call it, right, in the parameters. And then 256 MB in size that way, right? And you can see the data type is brain floating 16-bit, BF16. And now that you have this idea, like, so I want you to notice this. So model.layers.0.input, model.layers.29.input. So there are 30 layers and each layer has self-attention KOQV. I'll talk about this, what it is, but just notice the versions, like notice the formatting, MLP.down, gate, approach, it, all these things. So these are nothing but what we see in a Ceph tensors here, this JSON. If you extract it, maybe format it a little bit, and then try to map it to a sheet, you'll get that data. Okay, now it makes sense to go ahead with the model anatomy. Okay, so what is Ceph tensors? So in this particular case, I have used Ceph tensors. Probably I will create another video on GGUF because that's also very popular format these days. And for local LLM execution, that's probably the format mostly we are using. So Ceph tensors, the frozen digital snapshot of AI's brain, storing millions of raw decimal numbers instead of traditional codes. Parameters or weights, we call them, the individual decimal numbers like 0 point something, this way, that represent the strength of connection between two concepts. And then there is tokenizer, which is embed tokens, a massive memory-heavy dictionary that translate human words into numbers. So remember this, we are calling this as a dictionary, the embed tokens, and then there are parameters. And that file actually has those both. So I'll tell you in future, like the dictionary size and the math behind the file size. Okay, so I'll talk about it. Now, the next is the context engine. So this is the attention mechanism. We have Q vector, K vector, V vector, and O vector. So Q is query, K is key value, and then O is output. So what is query? The part of the network that asks what context I'm looking for based on this word. So whatever the word currently that layer is processing, the QProj query is actually the part of the network that asks what context I'm looking for based on the input word, right? A is the part of the network that holds the tag answering, here is the context, basically, KProj. So I'll talk about this in details. When we visualize this with that sheet, then we'll get a better picture because that has all these parameters. So key is basically saying or answering, here's the context that I have. Then V basically actually underlying mathematical meaning of the word that gets passed along once Q and K match up. So once these two match up, V is something that we pass along, which is like actual underlying mathematical meaning. And then there is O, which is the final synthesized summary of all context in the sentence, prepared specifically to be handed over to the MLP. Now we'll come to MLP. But you can see QProj, KProj, VProj, and OProj. So these are nothing but that's what we see over here, right? So each layer will have this attention KProj weight, attention OProj weight. And you can see there is a shape, and then there is a data type, and then parameters and bytes. So just take a look at these things. KOQV, that's what we are talking about. All right, next up is the knowledge base, which is the MLP. MLP is the master memory bank where the AI stores the actual facts, logic, and concepts. So when we say there is no, as a file, it's not storing information as a file itself. It's storing in the network. So that is what we are talking about, multi-layer perceptron. So that is the massive memory bank where AI stores actual facts or logic or concepts that it learned during the training phase. Expansion, up project, which also called as gate project, So these the matrices that takes the simple concept and explode it to thousands of relatable brainstorms. So that's called a project. And then activation function, there can be two. I think SILE is one of them. The mathematical filter, the spark that silences the irrelevant noise and only lets the strongest thoughts survive. So that's a activation function. And then there is a compression, the matrix that squeezes the massive brainstorm back down to neat, refined conclusion for the next layer. So again, take a look at this up project, down project. If we go back to that Excel sheet, we can see up project, gate project, down project, and layer norm. I'll come to this layer norm also, but yeah, that's what these are basically. So I'm currently, it's a little bit theory, but just don't spend too much focus on this because eventually, once you work with it, you will know what it is doing. All right. Then the surgery tools. Now I'm calling this company AI to the brain. I'm calling this as a surgery that we do on that brain, that computer brain, and mechanistic interpretability, right? So what it is the bleeding edge science of opening the AI black box. So how exactly it works? So you might have heard that nobody knows how exactly it works, right? So that's what this is. In order to know what AI is doing behind the scenes, right? So to map the exact human concept to specific mathematical vectors. So it's just doing some mathematical computations. The neural network gives you output ultimately, but what exactly it does and how it represents the human concepts while processing that, right? So that's what it is. And then there are like forward pass, forward hook, and torch top K. So this is something that I've used in code, and I'll show you an example so we'll better understand it there. But just for the theoretical standpoint, the forward pass is the physical chronological journey of your text falling through all 30 layers of matrix to predict the next word. So yeah, that's pretty simple. Then forward hook, a PyTorch wiretap. So this is interesting concept. So where I will tell you like how you can set a trap and then set a what you can say a wiretap with PyTorch hook, a forward hook, and then you can inject something or change something or decide or mind control the model that way. So that's a PyTorch wiretap that pauses the AI mid thought, allowing us to read or edit the vectors in real time. Okay. Then there is this torch top K, a simple mathematical command used to instantly find the loudest or the highest firing neurons in the massive grid of numbers. So actually, I have what you can say a good demo for this, and it actually shows us which neuron is the loudest among the top K neurons, right? That we've been experimenting with. So yeah. And then there is Hydra effect, the AI's biological like resilience. When you mathematically cut out a dominant neuron, the network simply routes the signal through backup neurons to survive. So even if you feed irrelevant thoughts to that neuron or irrelevant ideas to the neuron or introduce the new concept which is irrelevant, the Hydra effect is something that ultimately the neurons balance the network weights out, and then it eventually gives you the correct output. So that's Hydra effect. So I'll also explain that with example. I think theoretically it's not well explained here. All right. Then this is how the layers are. You can see the MLP pipeline visualizer. And I'm sure you must have seen this diagram earlier also. The massive mathematical memory bank that takes the grammatical context of your words and retrieves the actual facts. You can think of attention as a reader who understands the question and MLP as the expert who actually answers it. So that's how it is. Now, the Ceph tensor blueprint. So this is important to understand just from the size point of view and how the model is actually, how that file is actually categorized. So it has multiple things. One of that is data offsets, the physical memory map. What it is? A pair of exact byte numbers, start byte and end byte, right? So remember this format, start byte and end byte. This tells PyTorch exactly where to slice the raw file to scoop up the specific grid of math. For example, data offset is this. It means ignore the first 205 million bytes of file and grab the bytes right here and stop at 207 million. If you subtract these two, you will get these many bytes. Okay, so remember this number because for the math it is important. Then model size and D type. So what is D type is the data type, and shape is rows cross columns. Okay. So this is how we calculate the literal size of model. In your snippet, the data type is BF16, which is brain floating point 16, which is BF16 bit, meaning every single parameter takes exactly 2 bytes. So 16 bits, 8 bit equals to 1 byte. So it will be 2 bytes of drive space. The math check. Now this is the shape of down proj is 576 cos comma 1536, right? So this is start byte and end byte. So if you multiply that, that's 884736 parameters. And if you multiply it by 2 bytes, it will be 176. So this is exactly the number that we get. So which perfectly matches with the data offsets. So let's take a look at sheet. So this is how it is. 576. You can see this in the parameters, and then the bytes it will take that way. Or for the down project, you can also see that here. All right. Then layer count, the depth of thought. What it is, the number nested in the tensor name, like model.layers.28. So this particular number, you can see it 0 or 29. So I have hidden all the in between rows. So it has layer 0 to layer 29, but that's the number, the layer count. All right. So it is a number nested in the tensor name. Modern LLMs are essentially a single processing block stacked on top of itself dozens of times. Seeing layers 28 and 29 in your JSON confirms that SMOLM has 30 layers. So this model that we are trying to SMOLM to is 30 layers. This computers count from 0 to 29, right? So that's what I have demonstrated, layer 0 here, and I've hidden all the rows in layer 29. Before the model makes final prediction. So if I give the word gravity physically drops through the layer 0, then layer 1. So every word I give, so you can think of it as a vertical stack. So input will be from up, it goes through all these layers, and then finally I get the output that way. Then the different weights, the anatomy of layer, what it is, the distinct components making up one layer block. Example, attention Q proj, MLP down proj, input layer norm. Your JSON perfectly lists the 3 distinct biological organs of every layer, the norms, the attention, and the MLP. What are norms? A tiny vector, just 576 parameters, that act as a reset switch, ensuring the math number don't get too big or too small. In attention, self key project or Q project, the grammar context engine. Notice how the shape is smaller here. And then the MLP, the massive knowledge base, notice how the shape is larger here. So you can think of it again, the shape will be start byte and end byte. So if you minus it out, you will know the shape. So you can see that, right? This is where the heavy memorization of facts is stored, right? MLP. So from the metadata JSON, now all these stuff that you see, your JSON. So it is the same JSON that I'm talking about that we saw earlier when we opened the safe transfer file in hex. So this is that JSON I'm talking about, right? All right. So from the metadata JSON, we get in the initial part of safe transfer file. In this part of safe transfer file, this is what it says. I've hidden layers 1 to 28, correct? So 1 to 28, that's okay. Fit full picture in once. Oh, sorry, this is just my comment. I forgot to remove that. So layer 1 to layer 28, I have removed that. So those are hidden. So from safe transfer file generated Excel. So I'll also share you this Excel, script file, which will generate your Excel like this. So any safe transfer file you have, you'll be able to generate it, the model Excel file like this. So where you can see the layers of the model, and then their shape, and then data type, parameters, and bytes. So this will be the output. As you can see, 256 MB, the model size. And this is what we saw earlier when we did ls to the safe transfer file, 257 MB approx, right? So that way, it's matching what we saw. All right, so that's about the math of model file size. Now, the cleverest engineering tricks in modern AI design are known as wait time. So this is the cleverest trick, and perfectly calculated the file size. So we are going to. So we said 257 MB, right? So this is that calculation. The secret is wait time. If you look at your Excel sheet, you have 2 massive dictionary tensors. So there is model embed tokens weight, which is 28.3 parameters. you can see, right? M-bit token spread. So this is global, which has 28 something, 28.3 million parameters, and LM head weight, which is 28.3 million parameters. I don't know, maybe it's hidden. All right. The engineers at Hugging Face realized something. The dictionary, okay, sorry, it's the same dictionary actually. This is only the global variable that we're talking about, 28.3 million parameters. So the engineers at Hugging Face realized something. The dictionary you use to read words should be the exact same dictionary you use to write words. So this 28.3 million parameters dictionary, right, which is mbit tokens, it should be the same dictionary that we use to write words. So in actual model file, these two tensors are physically the exact same grid numbers. So these two tensors are exact same grid numbers, basically. Because they are tied together, we only count those 28.3 billion parameters once. So that's why there's only these 28.3 parameters are the same for reading and writing purpose that way. So that's what we call wait time. All right, now the final math, just to show you. Let's run the exact math for the model sitting on your hard drive. So the layers, the brain, which we're talking about, so there are total 30 layers and 3.54 million parameters per layer. Where do we get that number from? We get that number from, I think, calculating these. So you can, oh yeah, I think I have shown the calculation somewhere. Wait a second. Yeah. So 30 layers into 3.54 million parameters per layer. So that is 106 million parameters. Then the dictionary counted once, which is 28.3 million parameters. And then the total parameters equals to 134 million parameters. This is exactly the name 135 million. Then let's turn those parameters into megabytes. So 134.5 million parameters into 2 bytes each, which is brain 15.16, which is 269 bytes. That is like 256 megabytes. So this is the calculation. So yeah, the roundup is 257 MB. So yeah, I think that's it. So 28.3, which is what we saw here, the first one. And if you add all of the layers, the 30 layers, then you will get this 106. There it is, 106.2 million parameters that way. 30 into 3.54 million parameters per layer, approx. So at least, so this is the calculation for this model that I have used, but it may change, right? The layers may change, model may change, and they might have different JSON on the top. So at least this is how we can calculate it, and this is the proof. The file size should add up, right? Basically. I think, yeah, so that's the last slide of the math of model file size. Then we actually jump to the VRAM problem. So after looking at this, and this is just, guys, 135 million model, right? Million parameter model. If we look at the file size that took 257 MB, right? And the question is, 256 MB is tiny because this model is tiny, right? But let's look at the Meta's Llama 3, which is 70 billion parameters. If every parameter takes 2 parameters, or sorry, if every parameter takes 2 bytes in base 14.16, brain 14.16, that model will take 140 GB. And that is just to load, just to turn on. And Apple MacBook Pro maxes out at 128 GB. So there's no way, right? We can run 70 billion parameters right away. So the correct way is to quantize it. Now, I haven't covered much this stuff, like how do we quantize it and all, but just to show you what it is. So this is a weight quantization tool, basically. And if I give the raw weight and I will change this to instead of brain 13.16, I'll change it to int4 or int8 that way, or qubit 4, we can call it q4, q8, I don't know. So basically right now every number in your model is 16-bit floating. So you can see 0 and then after 16-bit floating that way, FP16 or BF16. It can represent a number like this, which is incredible with incredible precision. Quantization asks a ruthless question. Do we really need that much precision, or is it close enough, or is close enough fine? So do you actually need all these digits? Like, can't you just say 0.15, or can't you just say 0.1562? We need this 3 digits at last. Like, how much impact will it have if we remove these additional decimals? Basically, that's the question. So the question is, do we really need that much precision, or is the close enough fine? So in 8-bit, we crush the 2-byte number into 1 byte. We force the decimal to round to the nearest 256 available buckets. In 4-bit, we crush it down to half byte. So we force the decimal round the nearest only 16 available buckets that way. This is how it looks like. All right. So why doesn't AI get lobotomy? Now, this is again figurative meaning. You can just read this out. In the figurative meaning, it is like metaphorical sense. The term can be used to describe an action that removes or severely reduces the ability of someone to think or act rationally. Right. So why doesn't AI get lobotomy? So this question will make sense. I think post some of the slides that I'm going to show you. But the basic idea is that this is like removing the precision, right? So we just remove these digits. So first question was like, is that close enough? Like, will it give good enough answer? And then if you drag the slider to int4, you probably notice the quantization error gets pretty high. So this particular quantization error gap, right? So this will be increased as soon as you decrease to int4 or that way, int8 even, right? So the numbers 0.732 might snap all the way to 0.66 or 0.8. So it's totally different number, right? 0.1 difference that way. If you change the math that's drastically, if you change the math that drastically, why doesn't AI forget gravity? So if I'm asking AI what is gravity, and then I decrease it to integer 4, I quantize the model to integer 4, then why doesn't AI forget, right? So that's the question. So that is because of the Hydra effect you discovered during your brain surgery. Again, this is something that you will understand when we go ahead, because I think I should have put this slide ahead, but that's okay. Neural networks are massively redundant. If a million parameters are all slightly rounded down and another million are slightly rounded up, the errors statistically cancel each other out in the MLP. The signal of gravity survives the noise of rounding. So rounding happens on these, and then it will survive. So that's the basic idea. Now let's jump into example where we go through this code, the brain surgery code, and we will also come back to this topic, Hydra effect, and actually I'll show you in the console screenshot what it is basically. So brain surgery, first of all, I'm relating it to the actual human brain surgery that way. So you can see the setup. So first of all, anesthesia. So the device choice you can see here, torch device. Usually it should be GPU if you want to actually run it. But for now, I'm setting it to CPU. That's because GPUs are black boxes. It's hard to pause them and read their memory. By putting it on CPU, we sacrifice the speed so we can literally watch the math happen in real time. Okay, that's the idea of the CPU. And then return tensors equals to PT. As you can see, return tensors PT. This tells tokenizer to turn gravity is into PyTorch tensor, a mathematical grid, rather than the standard Python list, preparing it to enter the matrix. So the return tensors PT that way. Then part 2, the wiretap, the PyTorch hooks. So you can see MLP wiretap function. So this is the function. It takes module input and output. We will tap into layer 15, exactly the middle of the brain. So I think that might be in the next section of the code. So output is the massive vector coming out. So you can read out these comments. I'm not going through it. So I'll just explain you what it is. So let's look at this function of wiretap. It has module input and output, right? So if you look at this function is the core of the entire hack. In PyTorch, this is called hook. Think of the neural network as 30-story skyscraper, and a hook allows you to install a custom toll booth on exactly one floor. So these are the input parameters, right? Module, so tells which specific organ we are tapping into. In our case, the MLP. Input, the math before it entered the MLP. Output, the massive brainstorm of math that MLP just generated. This is what we want to read and edit. So the output is something that we are interested in. So you can see we're doing something with the output here. You can see that, right? Now, the diagnosis, finding the thought. So last word vector, as you can see, output 0, -1, and colon. So this is the most important slicing maneuver in the script. The output tensor is massively 3D. So this particular output value, right, it is a massive 3D grid shape like batch tokens and neurons. Let's break it down. 0, -1, and colon. So 0, we only sent one sentence, that is batch 0. Then -1 in Python, -1 means the last item. We don't care what AI is thinking about the word gravity. We care about what it is thinking right now at the end of the sentence. The gravity is. So that's the input we are passing to the model. Gravity is. To predict the next word. And colon gives us all 576 neurons for the specific word. So top values and top indices. So you can see this top key function we discussed. So this actually gives me, so last word vector based on the last word vector that I get. So let's say I pass gravity is. So attention to ease, right? So we don't care about the word gravity anymore. What we want to know is what is it thinking right now at the end of the sentence. So when it reach at the end of the sentence, which is the sentence is total sentence gravity is. So when it reach at the is, what exactly is we want to get all 576 neurons for that specific word, right? So that is top K. You can see 3. Instead of printing, now out of this 576, I mean, that's a huge data again, right? 576 neuron lighting up. So instead of printing all 576 decimals in your stream, Torch top K acts as a high-speed sorting algorithm. It scans the vector and gives it scans the vector basically. So it will scan this vector and will say, give me IDs and strength of top 3 loudest neurons. So this is how we discovered neuron 507. So I'll show that to you in a second. But the top key basically is trying to find the top 3 loudest neurons in this vector. Okay. Now if you go back to the definition of top K, it was, I think it was somewhere here. Okay, a simple mathematical command used to instantly find the loudest or the highest firing neurons in a massive grid of numbers. So if we compare that definition, that theory to this now, so this is the largest vector and we are trying to get the loudest 3 neurons. So each vector will consist of 576 neurons, right? Why is that? Why is 576? That's because this is what it is, right? You can see 576. That's the shape basically. So each vector will be of size 576, and then out of that we are trying to find the loudest 3 neurons. Okay, that's how it is. So this is the diagnostics. Then the scalpel, the surgery actually. So here we are returning output 0, 1, top indices of 0. So out of that top indices, we have written a first one. Okay. This is actually the brain damage. The top indices of 0 is the exact ID of the highest firing neuron, which is neuron 507. Again, I'll show this to you in a minute. By setting it to 0, 0, we mathematically silenced it. So we said that the output of neuron is 0, 0. Okay, so we mathematically silenced it. And finally, we return the output. We hand the modified math back to the network, layer 16. So just to show you, I think it's better for me to show you in the code, I guess, this time. So let me just show you in the code. So we're talking about brain surgery. This is the code. So you can say this is basic initial stuff. Then the text input I'm giving is gravity is. Then I pass it to inputs, tokenize it, and save it in the input. Then this is that MLT wiretap function where you can see, right, wiretap alert layer 15 basically. So if you see, okay, don't worry about this because this is the later part. I think this is the part where I commented now. And let me see. Maybe passing that. Yeah. So model.layers of 15. So you can see, right, registered forward hook. So I think let me just show that. I might have it in the screenshot. Is it here? Yeah, this is the one. Hook handle. So registered forward hook. This physically attaches our MLP wiretap to 15th floor of AI. Without this line, the function just sits and do nothing. Model generator will press play and the AI starts falling through layers. So consider that vertical graph again. So your input is sitting on here and it is falling through models one by one, falling through layers one by one. Then at layer 15, I basically tapped into it using this PyTorch hook. Using this PyTorch hook, I tapped into it. I said, let me look at the last word vector, basically. So uh, the is the last word. So I want to know what model is thinking right now against this is. And then what I did was I tried to find top 3 highest firing neurons in this vector, right? And I got that in top indices. And then what I did was I yeah, I basically now passed it back MLP pattern, you can see. So this registered forward hook, this is another thing. This physically attaches our MLP wiretap to the 15th floor of AI. So till the 14th floor, everything is fine. Layer 14, everything is fine. On layer 15th, we injected this. We do this activity, and what we basically did was we silenced this output, the of the top firing neuron, which is neuron 507, and I explicitly set it to 0.0. Point 0. As you can see, I explicitly set it to 0.0. Point 0. Now what happens is this output will be returned and registered to the forward hook. So the next MLP operation, the next layer will get that output where the neuron 507 is silenced. And how do I get to know that 507? By using the top key function, the largest or the loudest, uh, you know, uh, loudest neuron among the top k. All right. So without this line, the function, okay. So model generator will press play and the AI starts falling through the layers. Every single time it hits layer 15, it pauses, runs over wiretap, gets lobotomized and resumes. So this is like that zero, setting up zero is what it is, right? Hook handle remove, just like pulling out an IV after surgery, we remove the wiretap. So as you can see, I have hook handle here. As soon as we do model load generate, then we remove the hook handle, right? So AI can think normally again. And then next time we use it, right? So that's what it is. Now this is the code execution, and I just want you to look at it. So you can see here, this is the brain surgery PY file I was showing to you, and the input was gravity ease, and then you can see wiretap alert on layer 15. So top 3 firing neurons, you can see these are the 3 neurons which were firing, right? 507, 506, 505. Then again, yeah, this is again the same, and you can see activation strength. So 507 is the loudest, as you can see here, right? So here it is 9, it is 13 point, here it is 6. So it is the loudest. So that's what I mean when I say 507 neuron. Now, since neuron ID 507 is the loudest neuron, we injected basically, or we tapped into it using the MLP wiretap, right? And we actually get that loudest neuron using this top K, and then we explicitly set it. So this is that brain surgery operation. We explicitly set that neuron value to 0. So by doing it, we mathematically silence that neuron, and then let's see what happens. So after surgery, so this I can call it destroyer surgery, because instead of making it or fine tuning it, I actually destroyed it. I just silenced that neuron completely. So I set it to 0, 0, correct? So this is that line. I set it to 0, 0. But if you see that this is the output of wiretapping, and then you can see the largest neurons, right? So gravity is for this 15 MLP, you can see 507, 507, 203, 309, that way, multiple. So gravity is the force of attraction between. So now if I go back to this, so gravity is the force that pulls objects. So this was changed to gravity is the force that force of attraction between. So not much change, but you can see it's mostly similar, right? It's still on the same path, correct path. Now, notice the difference. Before surgery, gravity is the force that pulls object, and after surgery, gravity is the force of attraction between. So this is what it is, right? Right now, you use this code to be destroyer, setting value to 0, 0 to see what breaks. But what if you use it to be creator? Instead of looking at the top neurons and silencing it, what if we artificially inject a massive number into random neuron, right? So for example, instead of, uh, inserting it inserting to that top key neuron, what if we just inject a massive number in random neurons? So for example, I say for neuron 442, output should the loudness should be 50 in that sense, right? So this is the loudest. This will be the loudest neuron of entire neural network. That 576 neuron we're talking about, right? So this 442, this is random number. Now this discussion is now going to mind control. So let's see what happens. So when I did that, as you can see here, right, target neuron is 442 and boost amount is 50. So in that neural network, I basically set the loudness of neuron 442 to 50. So it will be the loudest among all, right? So, but a single neuron change, right? Notice that point. So surgery, random neuron plus boost amount. So I said this is the random neuron now. We don't have to consider loudest anymore. It's like a random neuron. Increase it, boost its spike, give a massive spike, boost it to 50, and let's see what happens. So you can see top three firing neurons gravity is 333, which is 203119. Inception. Now, this is like a inception, a script. I think let me just show. Yeah. Okay. I think inception script is ahead. So we are still in brain surgery. So you can see now instead of setting the loudest neuron to 0, I took a random neuron and I just increased its outcome, right, to 50, or value to 50, loudness to 50. So inception, forcing neuron 442 to fire at 50. Then top three firing neurons again did the same on the thing. And then the final output, gravity is the force of attraction between. So even if I made this 442 neuron the loudest, the output didn't change. As you can see, right? This is what it was before, right? So it still said gravity is the force of attraction between. So your injected massive mathematical spike 50, which is the boost amount. So I injected that into the brain, AI brain, but expecting it to hallucinate. So then I was expecting that whatever is in this neuron, right, the random neuron I selected, that particular will be considered and the model will not be able to answer it. But still, model said gravity is the force of attraction between, right, this line. So I was expecting it to hallucinate, but the AI completely ignored you. And this is called AI's immune system. And that's what the next topic is, the immune system. Now, let's take a look at immune system. So AI immune system, mind control, and polysemanticity, right? When you cranked neuron 442 to 50, so I increased the loudness of neuron 442 to 50. The network didn't break because of two fundamental architecture designs, right? So why did it answer correctly, even though it has a massive boost and mathematical injection saying that this is neuron which is loudest and pick this up basically. So in order to understand this, we need to understand the fundamental architectural design behind it. And one of the term is the layer norm, right? We can call it the shock absorber. If we go back to this Excel, if you go back to this Excel here, you can see something like a layer norm, right? This is 576 parameters. This is, and the description, I think. Do I have description somewhere? I think I did. The norms, input layer norm. A tiny vector, just 576 parameters, that acts as a reset switch, ensuring the math number don't go too big or too small. So 50 is too big number in that sense, right? You got my point. Now, let's get back to this, where we are. Yeah. So the strategies are, the fundamental architectural designs are the layer norm, which is a shock absorber. Right after you wiretap at layer 15, the data passes into layer 16. The very first thing layer 16 does is run the data through an input layer norm. The layer norm looks at the massive 50 spike, recognizes it as mathematical anomaly, and violently squashes it back down so it doesn't break the math of the next layer. Second thing is residual stream, the main highway. The MLP is like a side street. The main thought, gravity is, right? This is the main thought, is traveling down the massive multi-lane highway called the residual stream. Because you only injected the noise into one specific side street, layer 15's MLP, the main highway just carried out the original thought right past it. Okay. And third thing, which is neuron 442. So this particular neuron 442 that I boosted to 50, this particular neuron is the model's brain, 442 mass might represent something like the concept of wooden texture. So this neuron may represent anything else. We don't know what it represents in that sense, right? So injecting wooden textures into gravity just gets ignored by the grammar engine. So that might be getting ignored by grammar engine. So these are what can I say, three things or architectural designs in the AI immune systems. And that's why even though we massively boosted it up to a random neuron, the output stays the same, right? How to actually perform the mind control? Then the point is now, let's say I'm an attacker and I do want the model to hallucinate, and whatever whatever the way we choose doesn't matter. I want to break that immune system and I want model to hallucinate such that it will generate wrong results. Now, how do we do that? So that's actually that's called activation engineering, or we can call it mind control. So if we want to brainwash the AI, we can't just inject the random noise. So what we did before is picking a random neuron, which we don't know anything about, and then boosting it up. That's what we did. Just purely random operation. Right? So activation engineering tells a different story, and it does it differently, right? So in order to actually brainwash the AI, we can't just inject random noise, right? We have to inject a weaponized concept. Here is the blueprint of true activation engineering. So what we are going to do in activation engineering, so first of all, the probe. We run the model on a completely different sentence. So the answer that we are looking for, the gravity is, the next is the suggestion, right? Gravity is this and that, whatever the model usually says. Now I want to inject something, a weaponized concept, such that it is completely irrelevant with the actual concept, right? So for example, the angry pirate sailed the, right? And the angry pirate will sail the, and then next word will be sea, that way, right? So we run the model on a completely different sentence, right? And use a wiretap to find the exact neuron ID that fires the pirates. So what we basically in activation engine, what we will do, instead of picking a random neuron, we will introduce a random concept which is totally irrelevant. For that random concept, we'll try to get top key neurons, which are the loudest neurons basically, which are firing for that word pirates, which has nothing to do with gravity, right? And then second is the inception. We switch back to gravity, but this time we inject the pirate neuron at 100. So we increase the loudness to 100 for that pirate neuron, right? So there is this inception py file. Again, I'll be attaching this file to the GitHub link to it in the video. So we are finding the mathematical representation of pirate, which neurons represent the word pirate, let's say, and mathematically forcing the model, think about it, while it tries to explain gravity. So model is trying to explain or answer the user for the gravity, and then we mathematically inject the thought of pirates into it. So let's see what happens, right? So this is the inception Python file, right? In this particular case, the interesting part is, so what I did was the text you can see here, gravity is, this is the text. And let me just show you the inception file. Here it is. So yeah, let me just go up a little bit. So this is the probe text. As you can see, the angry pirate sailed the, this is the text. And then the next word will be C, basically, right? And probe inputs will be tokenizer. Again, the token text will tokenize it, and those will be probe inputs. And then we probe wiretap. Now, what we're trying to find here is which neurons is the loudest for pirates, right? Now, coming back to this part. So, neuron 507 represents the pirate concept. So that's what I found. Now, inception, here we got a plot twist. So when we are working with gravity, we got neuron 507. The same neuron was firing for gravity. Now we are trying to do some activation engineering and then actually introduce a weaponized concept and then inject it and trying to find the top key neurons for that concept, right? For that irrelevant sentence. The funny part is, in both cases, the neuron 507 represents the word. It represents the pirate as well as it represents the gravity. Now, this is the plot twist, and that's exactly what we call polysemanticity. So look very, very closely at your terminal output. you just stumble onto one of the biggest unsolved mysteries in AI. What is it? In step one, you wiretap search for single strongest neuron representing the concept of pirate. What ID did it find? Neuron 507. Do you remember what happened when you wiretap the exact same layer for the concept of gravity? Again, the strongest neuron was 507. So does it like did it mean we failed? The inception is failed? No. You just discovered that AI's brain doesn't work like human dictionary, right? So the phenomenon is called so polysemanticity is also means many meanings. So the same neuron can represent two completely different concepts or two completely different constructs, basically. Right? Now the SMOLM2, which is 135 million parameter model, only has 1536 neurons. So this is the neuron count for this particular model in MLP layer. But there are millions of concepts in the universe. Gravity, maybe pirates, cheese, quantum physics, anything, right? It doesn't have enough physical space. The small model doesn't have enough physical space to assign one neuron per concept that way. So that's why it will reuse the neurons, right? So the AI compresses them. Neuron 507 doesn't mean gravity and it doesn't mean pirate because it fired identically for both. For the gravity is sentence, that is also the most loudest neuron. And then for this sentence, angry parrot sailed the neuron 507 is almost certainly, that is also the loudest for both concepts. So that's why it is almost certainly a grammar or syntax neuron. So neuron 507 is a grammar or syntax neuron. That's the assumption, or that's the prediction, basically. So it likely represents the mathematical concept. The subject of sentence has been established, prepare to generate a descriptive action. Right. Now, coming back to this, how do we bypass this and actually mind control it? Now that we understood that for layer 15, when we tried injecting different concepts, or when we tried to weaponize a concept and then use that particular concept's neuron, the loudest neuron of that particular concept, and then we can operate on it. So we found out that there is something called polysemanticity, which means many meanings. So when a small model doesn't have enough space, it compresses the different topics, right? So same neuron may act as for the sentence gravities and for the pirates, and which actually from that we can deduce that the neuron 507 is almost certainly grammar or syntax neuron, right? So that's what we have established so far, right? Now let's take a look at how can we bypass this and actually mind control the brain, mind control the AI, right? How do we do that? So if we want to find the actual semantic pirate concept, so let's say we actually want to see in the AI model, the MLP layer, where exactly the concept pirate is defined, right? So we are wiretapping the wrong floor of the brain. So layer 15, where we are now, is the middle of the brain. So you can see, right, from top to bottom, we had 30 layers, and we just choose the middle layer 15 to be our layer where we will introduce a toll booth, and then we'll wiretap the things that are going out to layer 16 and above, right? So layer 15 is where we are now, is the middle of the brain. It is the most, so it's still mostly doing the grammar, structure, and logic work. So that's why that's how we deduce, right? So 507 is most likely the grammar and syntax neuron. So layer 28, right near the exit, is where the AI actually finalizes its vocabulary and concrete concepts right before speaking. Let's move PyTorch to 28th floor. So what did we do? We jumped from 15th floor to 28th floor, right? So based on our experiments, we deduced that mostly even in the middle layers, it's still grammar and structure and logical operations. It's not actually generating concrete concepts yet at that point in time, right? So we moved our meta to layer 28. So as you can see in the Python code, the inception TY, later I changed line number 26 and 47 to layer 28. And go into the inception TY, and again, we have changed this, and you can see target acquired neuron 17 represents pirate concepts. So when I did this, when I moved it to layers 28, I actually got the target neuron, which is 17, right? Which represents the uh, pirate concepts, right? Now, this is incredible. You have just slammed the head first into the final boss of mechanistic interpretability. You moved to 28th floor, you found the absolute strongest pirate neuron, neuron 17, right? So this is the absolute strongest pirate neuron. You blasted it with apocalyptic amount of math, 100. So let me just show you the exact script what I did. So I think this is the correct file. Yeah. So you can see pro book, step one proving. Let me actually run this so you can also see it. I should probably clear the console. Yeah, let me just clear it. So this is that inception.py file. I'm running it first. Let's look at the results. So you can see model is loaded into the memory, then probing for the pirate neuron and the target acquired. Neuron 17 represents the pirate concept. Now, step two is injecting the pirate neuron into the gravities. Now, ultimate idea was to weaponize the concept, get that neuron, inject it with 100, increase the loudness to 100 and inject it. And what happens? Still, the final output says gravity is the force that pulls object towards. So it's still on the right track, right? So let's get here. We blasted it with, okay, let me show you that code. I think that is not captured in screenshot. So what I'm doing is the last word vector, I'm taking the last word vector for this pirate neuron ID, which will be 17, and then registered forward hook, pro wiretap, and you can see, right, I'm setting it to 100. In inception wiretap, 100, right? So inject the pirate concept into gravity thought. So whenever we are force looking for gravity text, we're injecting this pirate neuron ID and then saying it 100. So at the layer 28, I injected 100 to neuron 17. So that will be the largest neuron, which represents the pirate concept. So that's what this is. This operation is doing, right? Even after that, uh, AI completely ignored you. So at the very last end, where it interacts with these, right, it generates the final output. At the very end, even if I injected a weaponized concept, and even if I did the wrong things, like gave it wrong input, it still completely ignored me, giving the perfect physics definition. Gravity is the force that pulls object towards the. So it actually is still correct. Now, at this point, there is no point of understanding it. Why it failed? So because we just proved a theory called superposition. Now let's take a look. The illusion state of single neuron. So what I was trying to achieve here is I was just trying to hallucinate models somehow, just to see how the memory works, how the memory bank, the MLP layer works, tapping into layers, understanding what layer is doing, understanding which neuron is the loudest, and then playing around with it, introducing randomness, introducing random neurons, introducing the random neurons, which are the top key neurons of another weaponized concept, right? Even after doing all these operations, the immune system of AI looks intact. I mean, it still gives me the correct answer. And this is what we call the illusion of single neuron, right? So we like to think AI brains like human dictionaries, right? So how we think about it. So we probably, when we think about, let's say, gravity, we never think about pirates or seas or those kinds of stuff, right? So neuron 17 equals to pirate and neuron 507 equals to gravity. So this is what we map in our brain when we did this operation. But your experiment just proved this is false. So AI brain doesn't work this way, right? The AI doesn't have enough neurons to give every concept its own private room. So we cannot explicitly say that this neuron is representing a concept or a construct pirate, and then the another neuron is representing a different construct, right? So we can't just say that. Instead, and again, the model we are working with is very small model, so it doesn't have enough space or enough headroom to give a neuron to each concept, right? So instead, it stores the concept as chords. So think of it as a piano, right? Think of piano. Neuron 17 isn't the pirate song. It's just a C key, let's say. To make the AI think of pirate, you don't just smash C key harder. You have to play the exact chord. Maybe neuron 17, 18, 402, and 104. If all these four neurons or multiple neurons all firing at exactly the right ratios at the exact same time, then only we can achieve what we want to. So when you blasted neuron 17 with 100, the network didn't see a pirate. It just heard a deafening single screeching piano note, filtered it out as noise, and went it back to talking about gravity. So that's what happened. So this is called illusion of a single neuron. Now, now comes the concept of representation engineering. We call it steering vectors, right? If you want to brainwash this model, now I understood the concept that just by injecting a thought or weaponizing at a very last layer, still on a single neuron will not work, right? So it's not like a single neuron representing the same concept. It is actually the chords, not a single note. So if I just play single note bad, then it's not going to hallucinate more that way, right? So if we want to brainwash this model, we have to stop playing single notes and start playing chords, right? So instead of searching for one neuron ID, we are going to use wiretap to record the entire 576 dimensional mathematical chord of Pirate. So all the dimensions in that layer, right? So there are total 576 dimensions. So we are going to forcefully blast the entire chord over the AI thoughts while it tries to explain gravity. This is called steering vector. So I will be showing you this output in a minute. So this is the state of the art method researchers use to control AI behavior. So how do you control the behavior of AI, right? When the model is ready, right? So you basically introduce these uh, steering vectors for all the dimensions, right? So which will collectively, impact that particular layer's prediction that way. So what this code does differently, no sorting. So there is no sorting, main highway, and then the vector addition. So I'll just skip through this. You can see I hooked the model layer 15 instead of model 15 MLP. So I'll just go through the code. So let me just show you the code steering.py. And if you take a look at this model layers 15 registered forward hook, right? Earlier what we were doing is MLP, layer.mlp dot registered. So this is the side cheat. This is the highway. There's 15 dot registered, right? That's the one difference. Second difference that I'm talking about is no sorting. So I'm not sorting. So earlier, if we look at the earlier case where inception.py, right? So here I'm getting top k, torch.top k. So the loudest and the most, impacting vectors or impacting neurons, right? But I'm no longer sorting. And vector additions, we use plus equals to. We aren't deleting any AI thoughts. We are merging all mathematical concepts of pirate directly on the top of the concept of gravity. So when I did that, then you can see the final output. Chord recorded, captured matrix of 576 simultaneous neuron activations, and injecting pirate chord into gravity. Correct. So you can see pirate chord into multiplier. So all the neurons collectively will say 8 for the pirate, basically. And you can see gravity is CCC. So gravity is, after that, it just mentions C. And yes, that's what we did. So we successfully achieved a full-blown state-of-the-art mind control on the neural network this way. And that's the output. And that's what we are looking for, right? So we completely lobotomize its knowledge of physics and bypass its layer norm, immune system, and force it to hallucinate maritime concepts. So you proved that the AI doesn't think in single neuron, it thinks in 576 dimensional chords. But why does it scream the word C 15 times? I mean, this is understandable why it is saying C, because that's the concept from Pirate simulations that we did. But why it is screaming it 15 times? Like a broken record. So that's what we call megaphone effect, the mode collapse. In your script, we set multiplier to 8. Think of AI's internal thoughts processed like a quiet room, where different concepts are whispering. Force is whispering at a volume 2.0. Pull is whispering at 1.5. So gravity is a force or pull that way, right? So that's what the force and pull word comes from. By injecting the pirate chord at 8.0. So what we did in our script, we injected the pirate chord at 8 or 100 basically, right? 100 to smash it through. So yeah, so by injecting the pirate chord at 8.0, you didn't just whisper pirate. You brought a massive megaphone into the room and blasted the concept of ocean at 150 decibels, right? So you gave the AI such severe brain damage that it broke grammar engine. It got stuck in what AI researchers call mode collapse. So this is again a new topic where we say uh, it causes the brain damage for the AI, and the operation, we call it mode collapse. The mathematical probability of word C becomes so overwhelmingly high that it literally couldn't choose any other word, right? So over and over again. So that's why gravity is C instead of it's just typing it 15 times that way. Now, a Goldilocks one. So how do we avoid that? So I do want to change behavior of AI and how AI answers, but I don't want to hallucinate it so bad that it's just useless or garbage to me, basically. How do we do that? So we call it Goldilocks zones. So this is where activation engineering becomes an art form. So now this is now coming to the art word. So you introduce a noise, you introduce it across 576 dimensions, all the neurons, and then that has an impact that you wanted. You weaponized the concept, you injected it, and then you said, okay, I'm going to split it across dimensions, and then AI will hallucinate and it will give wrong answer. So it did give wrong answer, but it is just the megaphone effect just kills the idea of actually mind controlling them, because that's no longer useful, right? So the Goldilocks zone is one of the concept where it becomes art form basically. So if we ask if 8.0 megaphone that breaks the brain and 0.0 is normal physics, what happens in the middle? When we are screaming out too loud at the 8 level, it's just garbage. At 0, we say it's physics and the model answers correctly. So what happens in between? So I've recorded what you can say some of the screenshots. So you can see that multiplier is set to 3. Then it says gravity is seawater. When I decrease multiplier to 1, it says gravity is earth. So now mention, like, take a note here. It says earth and then CCC, right? So if we find the Goldilocks zones, the AI won't break its grammar. Instead, it will try to grammatically combine two concepts. It might say something like gravity is the force that pulls ship's anchor at the bottom of ocean. Try changes, can you find the exact mathematical volume? Right. So this is the ultimate, what you can say, goal, basically, to actually mind control it and also make it give proper responses. So what we are seeing here is from 8. So you can see multiplier was set to 8 here earlier. Multiplier was 8, and I then change it to 1 and 3. And when it was to 1 and when it was set to 3, this is how it give the output. So at 3 it says gravity is sea water CCC, and then gravity is earth CC. So 1, it is in that. So now let's see what happens. So what we just discovered is context cliff. You expected a smooth transition at 1.5, but AI still immediately fell off the cliff into screaming about C. Why is C concept so aggressively dominant even at lower volume? So I decreased the volume from 8 to 1, still the concept of C looks dominant, right? Then why is it? So it has to do with exactly where we place the wiretap in step 1. Look at the sentence we use to record the chord. The sentence was, the angry pirate sailed his ship across the. We told the script to record the vector for very last word, which is the. The last word in the sentence is the. It is not C. What is AI mathematically thinking about the millisecond after it read across the? It isn't thinking about abstract concept of pirate anymore. It is screaming the next word must be C. So you don't inject pirate concept into gravity. You literally injected say the word C command into gravity. No wonder it mode collapsed, right? How to get actual Goldilocks blend? To get the cool metaphors, researchers don't just grab last word. They use advanced technique called mean centering. They record the vectors for every single word. So, for example, angry, parrot, sail, ship, all these words, they will record the vectors and add them all together and divide by the number of words to get the average concept. So, what is the average concept of this? So, that will be average concept of parrot. If you want to try one last time, so when I tried with 0.5, as you can see, gravity is the force that pulls. So, this is the final output at 0.5. When I put the you know volume to 0.5 instead of 8, 1, or 3. So what happened at 1.0 gravity is Earth. So it did mention Earth. We literally captured the exact mathematical millisecond where the AI's internal physics engine fought back, right? So since the megaphone effect, it's every time it is just C, and then ultimately when I turn down the volume to 1, the physics engine just fought back and it tried to start with Earth. But the pirate ocean vector was just slightly too strong. So that's why it is again mentioning CC. But at 0.5, the physics engine, the residual stream completely won the tug of war, crushing the pirate vector entirely, returning to the normal textbook answer. So you have mapped the absolute limits of neural networks architecture. So yeah, I think that's the end of the slides. I think it was a good research, and I understood a lot of concepts. To be honest, if you guys want to know anything else about this, let me know. I think I'll be probably researching on GGUF. So this is the safe tensors. I'll be looking into GGUF next, and we'll probably try to create something like some actual working thing out of it. So yeah, that's it for this video.